Ladies and gentlemen, we are going to talk about kinematic experiments and using the UAM or kinematic equations. So I had a question. I was thinking the other day, my little girl is getting older, and I wanted to know, how fast is Harriet? So I thought I could do an experiment to figure this very thing out. So what I decided to do was have Harriet do some running. And I wanted to measure how fast she is. How fast is typically velocity? So I knew velocity, and we'll talk more about this later, is change in position over change in time. So I laid out cones on a little course for her to run. I measured the time it was going to take for her to reach each cone with a stopwatch, and I measured the position to place the cones with a tape measure. I'm being very explicit here because when you're describing your experiments that you're going to be doing and explaining, this is how you should be, the detail you should go into. You should make sure you're saying exactly what you're doing, what you're measuring, and what you're using to do the measure. So then I had her run. 2, 1, go as fast as you can. Go, 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 go. From that data, I was able to figure out, and using video analysis, but you could do it with just a stopwatch, her times and her positions at the various times. The positions were 1 meter, because each one of those cones was at 1 meter, and then how much time it took for her to reach each of these cones. Now, I've got this data. How do I figure out how fast she is? Well, I put it into graphical analysis, and I get this data. Okay, that kind of looks linear. I've seen some ugly linear graphs before. You're probably thinking to yourself, because Mr. Chamberlain has made you do that. My first note that this is not linear is there's a big gap, and I don't know, that's a nice slope. So I'm going to apply this curve fit. Okay? So first thing I'm going to do is look at this. Okay? So, okay, I can see how it's aligned, but I don't know that it's exactly aligned. This RMSE means root mean squared error. So the big thing that you should take away from this is that there's quite a bit of error here. It's 0.4495. So maybe I'll try a different curve. Let's try a quadratic curve. Okay. So I look at that. That fits pretty darn nicely. And I can even check the error against it. Here, I see 0.03. All right, 0.03. That is quite a bit smaller of an error compared to this linear model, the line. So I'm going to guess that this is quadratic, meaning she does not have a constant velocity, which a flat slope would show. It means she has a changing velocity. So that leads me to the question, how fast can Harriet accelerate? Because she's changing her velocity, so she is accelerating. Well, to do that, I need to figure out her velocity at each one of those different points. So I need to find the instantaneous velocity, not the average velocity, but that instantaneous velocity between each cone. So I need to know the change in position over the change in time. That delta t should be over here. So to figure that out, I know that, say, between this is the 4th meter and this is the 5th meter of her run, its final, a change is always the final minus the initial. So it is 5 meters minus 4 meters over the change in time, which is 2.75 seconds, I timed out, minus 2.4 seconds, So it's 1 meter over 0.35 seconds. That gives me 2.86 meters per second. Now, this is just her velocity over this time period. That's just her instantaneous velocity between here and here. If the smaller those positions are, the closer we can get. But we can calculate her instantaneous velocity to be this, 2.86 meters per second here. So if you were to write in your methods, you would say, to determine the velocity, I calculated the change in position over the change in time. I did this calculation. I figured out what the change in positions over the changes in times are going to be for each position. And I see, okay, I see that. But how am I going to know how much it's changing? Well, you can graph. So I took that data and I put it into our friend Graphical Analysis, and I looked at what it looked like. All right, so this is looking a little bit more linear. We apply a linear fit. We see a much lower error than we saw before, and we have an acceleration now of 1.039 meters per second squared, because the slope of a velocity time graph is our acceleration. So I know my daughter's acceleration of 1.039 meters per second squared, and I wanted to know, maybe someone did a similar acceleration analysis for Usain Bolt, the fastest man in the world. Turns out someone had. They didn't show velocity, but someone from Wired magazine had looked at his speed over time and his record-breaking run, a 100-meter dash. They did that, and they looked at the slope, because the slope of a velocity time graph is your acceleration, and he's at 3.09 meters per second squared. Now, I'd say my daughter has a little bit of room to improve if she's going to become the fastest person in the world, but it's good to know he's only 3 times faster. So then I started thinking, how fast would Harriet be going if she ran for 6 seconds with the same acceleration? Well, I need some equations to help me make those predictions. Lucky for you, we have some. Now, I don't want you to write these down again because, in fact, there's actually a better form that I like in a nice little picker chart that I think is going to make your lives much easier. This is definitely what I would like you to write down, recreate this exact chart, make it in a way that you can utilize it, because it's going to make your life better when you want to predict motion. Now, this only works if the equations, or if the object has a constant acceleration. We showed a constant slope, so this is fine. And then it's got to be moving in a straight line. These only work if the object is moving in a straight line. So, and they're called uniformly accelerated motion, UAM equations. That's why I'm going to call them this. Just so you remember this, that it must be a constant acceleration for you to use it. If it changes acceleration, that doesn't count. So our equations are v equals at plus initial velocity, v naught. Delta x equals v naught t plus 1/2 at squared. V squared equals 2a delta x plus v naught squared. Delta x equals 1/2 v plus v naught t, all in parentheses. And then a new equation, which is like a special version of the first equation. Don't get them mixed up, but it's like a special version of the first equation, or the second equation, I should say, that delta x equals v naught t plus 1/2 at squared. We have delta x equals vt minus 1/2 at squared. Notice there's a plus instead of a minus, and instead of the initial velocity, like in the second equation, you should have just v, like in the final equation. Now, I had you wrote down the initial equations. I'm changing things on you, but I just want you to know you're going to see things changed a little bit. You should make sure you get this down too, so you know these things all mean the same. Within the same box, we have the same thing. So initial velocity is going to be written as v at time 0, or v naught x, that means just in the direction x, because we're going to talk about the y soon, or vi for v initial. Final velocity is just v, or vx. Notice it's missing the o's because it's not at time 0, it's some other time, or just vf. Displacement, or change in position, is going to be delta x, or x minus x naught, or x final minus x initial. Acceleration is just going to be a with the x or without, and then time, you'll note, is not going to have an x or a y. It's just going to be time. But these all mean the same thing. So now let's solve that problem. So I want to know, how fast would she be going if she ran for 6 seconds with the same acceleration? So we know that her acceleration is 1.039 meters per second squared. That came from the slope of the VT graph. And that might be given to you, or you might get it from a slope. We know 6 seconds because it's given in the problem. And we actually know one other thing. You saw her. Oftentimes it's stated she started from rest. So we know her initial velocity is 0 meters per second. How fast means velocity. Is it the final velocity or the initial velocity? Well, we know the initial velocity. We must be looking for the final velocity. That comes from how fast means v. Now that leaves one equation, or one variable I should say, that we don't have and we don't need. I call this our dehudahun. Don't have, don't need. Because it helps us pick which equation is going to be the right equation to use. So let's go to our equation picker chart. We know that we don't have and we don't need our delta x, our x final minus x initial, our change in position. So this is the equation that we're going to use. If we had not had a final velocity or didn't need it, if we did not have or need our time, if we did not have or need our acceleration, we'd use this one. If we did not have our initial velocity or need it, we'd use our final equation. But we know we're going to use this one. So the equation is v equals v naught t, v naught plus so the equation is v equals v naught plus at. We know our v naught is going to be 0 meters per second. We know our acceleration from the data is 1.039 meters per second squared. We know our time is 6 seconds. And so we plug those in. And we get v equals 0 meters per second plus 1.039 meters per second squared times 6 seconds. Now, something that I want you to note, is we're going to have 6 seconds here in the numerator, and per second squared, I could write this like this, or I could write this like meters over seconds squared. And one of these seconds and one of these seconds is going to cancel out so that our units become meters per second, which is what we want for velocity. So our velocity becomes 1.039 meters per second times 6, which equals 6.234 meters per second. That is our final answer. That's what we would predict. How fast would she be going if she ran for 6 seconds with the same acceleration? Of course, she must be running with the same acceleration. And I also want you to note, we can solve any of these problems, even though there are 5 variables we're working with. We only need 3 givens. We need 3. I want you to remember there are 3 letters in UAM, and we need 3 givens in order to solve a problem with it. But that's it. We only need 3, and then we pick the equation and we solve. Now I would like you to solve how far would she be going if she ran for 20 seconds. I want you to try to solve it, and then I will show you my solution, how I would like you to solve it after the fact. How far would she have gone after 20 seconds of the same acceleration? So the first thing we need to figure out is what we know in this problem in order to make this prediction of how far. So we know from the problem, we can go right down here, it's 20 seconds, that is going to be our time. We know the acceleration of 1.039 meters per second squared. That's from the velocity time graph. Specifically, the slope of the graph. We again know she started from rest. And that's all we need. We need to find, because we have how far, delta x, and we don't need this. That's our dehudahun. We're going to go to our equation picker chart. We don't have and don't need our final velocity, so we're going to use that second equation of delta x equals v naught t plus 1/2 at squared. Delta x equals v naught t plus 1/2 at squared. We are going to plug in the things that we know that are our givens. We have 0 meters per second. We have a time of 20 seconds. We have an acceleration of 1.039 meters per second squared. And we have a time of 20 seconds. I'm going to put it in parentheses so you remember to do something with it. We're going to plug these in, and we have delta x equals 0 meters per second times 20 seconds, which just gives us 0, plus 1/2 1.039 meters per second squared times 20 seconds squared. Now, I want you to note this is going to go away because it's just 0. We have meters per second squared here. We have seconds squared in the denominator. We're going to square our seconds here, so they will cancel out, and we'll be left with meters, which is what we want for our delta x. So then we have delta x equals 1/2 times 1.039 times 20 squared. Which gives us a displacement of 207.8 meters. A reasonable number of sig figs. So I'm going to leave it. That is how far we would predict her to go if she went with that same acceleration for 20 seconds. Note that that is a very long time to keep up the same acceleration. Usain Bolt does not keep up an acceleration for 20 seconds. That's just not possible. He even flattened out, if you remember from the graph, which is likely to be the case. But she's a little girl. She's got a lot of energy. She does not accelerate that fast, not yet. And as such, this could be the case. Hope that was helpful. Go! Run as fast as you can. Run, 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 run. Run, 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 run.